Hello. Today we're going to talk about service meshes, different service mesh solutions, what is the service mesh interface specification and how it appeared. We're going to talk about a project called Network Service Mesh, which is a non-standard service mesh. We'll describe that later. And we'll say why our community wanted to integrate that with the specification with other service meshes, and talk about the traffic observability that we achieved with that. So how many of you are familiar with service meshes and what service mesh is? Okay, we are going to describe that. Service mesh is an abstraction layer on top of microservices, and it provides features like observability, discoverability, security, resiliency. The goal is that you don't need to implement all of that within your microservices, but instead you can adopt some of the existing service mesh solutions, and you can have all of those features on top of your microservices. And how it works, when applications are deployed like TOPS in Kubernetes, if you want more visibility how they communicate, this is not very well provided out of the box within Kubernetes. You don't have any information what communication is happening between them. You don't have control. You cannot prevent middle-in-the-man attacks and so on. And here, Service Mesh can help. How it works, it injects proxies. These are their containers within your pods, with your applications. And their end goal is to provide all that features that we listed previously, like resiliency, security, and etc. And this is very briefly what the standard service mesh is. There are different service mesh implementations. Linkerd is the official CNCF-supported service mesh project. Google, IBM, and Lyft provided Istio, which is known as the most popular solution, and it's built on top of Envoy proxies, the proxies that we showed in the previous slide are from Envoy. And new service meshes are appearing as well, like Kuma and Maesh are the newest ones that I read about. Few months ago, they appeared. Each of those solutions was separately developed its own API. And it's a bit different. For example, if you see the Kubernetes project, it became the standard for containerized applications. While with service mesh, it's a bit different because every service mesh is developed in a separate way, and all of them work well, and there is no service mesh for the moment that is established as the most common solution. And how many of you are architects? Any architect here? One. Imagine this situation. Imagine you have a deadline for a feature you want to provide. You already selected some service mesh implementation that you bounded to your project, and you find out that the feature you want to deliver for the moment is incompatible with that implementation, and you need to change it, but you have deadlines. And what's the result from that? Usually. This is how the idea of service mesh interface appeared. Having so many service mesh implementations with different APIs resulted in a need for a common specification that can unify all of them. The goal is to provide a common portable set of service mesh APIs so that you can develop your applications without the need to bound to any specific implementations, but instead you can make it compatible with the service mesh interface, and you can easily switch between different solutions. It covers some of the most common service mesh use cases, like it has specification for exposing metrics for traffic metrics that you serve for tools like dashboards and especially for dashboards and autoscalers. There is specification for traffic access control, which configures the access to specific pods and routes based on identity. There is also traffic spec specification. It serves for specifying on protocol basis the type of the communication. And we heard about SMI during KubeCon Europe this year. It was widely announced by Microsoft, said that it's a common effort, different service mesh communities participating in different companies. And we decided that it's good for us if we unify with the others. But we had some problem with that because our solution is a bit different. Service mesh interface is very well compatible with all the implementations that I talked about previously. But it works especially for HTTP protocols, but the network service mesh project is a bit different. And what's the difference? It covers another network layers. The standard service meshes cover the 4 to 7 layers of the OSI model, while network service mesh covers the lower layers. It's an infrastructure layer on top of your services that manages layer 2 and layer 3 service-to-service communication. It provides on-demand and negotiating point-to-point connections, and it exposes a gRPC API to publish and consume network services, and all of this can happen without any changes to the underlying CNI. I'll briefly share how it works in order to give visibility. Imagine, we're going to talk about what is a network service. Imagine this situation, you have an application that is running in some public cloud, and you want to consume some service that is in another public cloud or in a corporate intranet. And here we have a problem, because usually the application would have to implement the connection details within itself. And if you have multiple applications, and if those details change, you need to update your implementation in all of these applications. And instead of that, we offload that to a network service so that it can take care of implementing the communication. Using a network service, we would have clients that consume network services. We would have endpoints, for example, like the firewall and VPN gateway, you would need to go through in order to connect to the corporate intranet. And we have wires, which serve as connections and which are payload agnostic. Here is how we describe network service. It's something like somehow a topology of how your connections look like. You specify the payload. You specify source and destinations. For example, in this YML, source is specified as firewall, and destination from the firewall is the VPN gateway. And this way of service definition makes it possible to chain multiple clients and endpoints in order to provide the so-called service composition, so that you can describe a whole topology with as many rules as you need. And if that client from the previous picture requests such network service, it will connect to the firewall destination because it's described like that in the YML specification, and then it would follow the routing rules within that. And let's see how actually, what happens under the hood and how NSM differs from the other solutions. You remember the picture with the pods and the proxies. Here you have also typical Kubernetes deployment, and you have network service mesh deployed on top. You have your applications, which are, again, pods within Kubernetes. And here, in order to have connection, we specify them as clients and endpoints. Actually, I shared an example where a client wants to consume service and this serves as type of connection, but you can create layer 2 and layer 3 network within any applications, pods within your system just by specifying some of them as clients and endpoints. It works a bit different. Instead of injecting a proxies, here the endpoints, announce themselves to NSM. The client requests to consume a network service, and then network service mesh takes care of creating the communication by injecting network interfaces directly to the pods and creating a connection tunnel between them. And all of this happens without any changes to the underlying CNI. In a bit more details, there are two main building blocks within NSM. Those are the NS manager and the forwarding plane. They live in every node of your system. And the Kubernetes API server serves as a registry for network services. How the communication happens, you deploy your network service YML to the Kubernetes API server, and the whole topology is registered there. Then you have your client and endpoints. For example, imagine you have firewall that's an endpoint. The firewall will request a network service from its manager. It will announce itself to its manager. And the manager will register that endpoint to the Kubernetes API server. Then the client will request to consume network service, and the manager will send that request to the Kubernetes API server. And then it will find where the other manager is located. And both managers, after finding each other, they will start to negotiate the connection details between them. And once everything is set up, they will inform the forwarding planes. The forwarding planes will create tunnels between themselves. They will inject the necessary interfaces within the client and the endpoint, and with this, the connection will be completed. It can also work in mixed environment. On the one side, you can have virtual infrastructure, and the endpoint can be virtual machine, for example. But it's most basically how it works. And as you can see, it's different because other service meshes they just provide some top services for top solutions for microservices like security and etc. Like here, you create, based on gRPC protocols, you create point-to-point connection. And some of the most there are many use cases that it can be applied to, but one of the biggest use cases, this project was partially initiated by requirement from telcos, which want to adopt containers in order to use containers for telecommunication. So you can watch your cable TV, and the underlying infrastructure can be based on containers. And why we wanted to integrate with service mesh interface, we are very different from the others. It's also called service mesh because it's an abstraction layer, but actually it's very different. But we had two main reasons. The first is that we still want to be considered as service mesh, and we want to be compatible. For example, if someone is implemented their microservices and services compatible to the service mesh interface, they will easily adopt NSM on top of that. And another reason is that having supporting the SMI API would easily allow us to combine with the other upper layer service mesh solution and to provide the full OSI model on top of microservices. And what we did, we started looking for similarities. But what SMI has, it mostly supports HTTP protocols. We started to look for something we can match with. And the first thing we noticed was our metrics. We saw their metrics API, and we found out that supporting that in NSM can be important for us because it would give observability of what's happening with the communication. Because having network traffic without any metrics observability is like having your applications and containers without logs. And if something breaks, you cannot examine what's exactly happening. While here you can view the error packets, the packets, bytes that are transmitted, and etc. And what we found, we looked at how the SMI traffic metrics CRD looks like. So what they do, they just describe a metric name, like they use it for response latency, failure count, success count, and etc. They support units like periods, and they support values. And what we had by that moment was something like that. We actually, all we had, the forwarding plane that I showed previously, planes, they expose metrics, actually. They send with every cross-connect they create between client and endpoint. They share what traffic goes there, but the only place it's visible is in the logs. So imagine you have a problem, you have to traverse thousands of lines of logs to find your specific connection and to try to analyze that in order to see what's happening. And it's not the most convenient way. And what we found useful from the SMI, we saw their solution, how their API works. It's integrated with Prometheus. So if we support Prometheus, if we expose our metrics there, it's very easy from SMI to get that metrics from Prometheus, apply to their API, and be compatible in that aspect. And what we found out, our forwarding planes support metrics like that: RX bytes, RX packets, error packets, and TX bytes, packets, and error packets for every client and endpoint. So what we decided to do, we decided to use that as metric names. Instead of having success, failure count, response latency, we wanted to support that to see what bytes, packets, and error packets are transmitted from each client and endpoint. And actually, those won't be time units, but they would be the number of those values. But we had another problem with that. What was the walk that you previously saw was actually a walk from the cross-connect monitor, and it describes how the data that cross-connect contains. And the only information that we had was the network namespace, which is something like that. And it's not very human readable, non-convenient. If you want to see what traffic is going on between a specific client and endpoint, you need to start searching on what network interface it uses in order to identify that traffic. This is the only unique thing we had about this information about what is the client in that cross-connect and what is the endpoint. Yeah, that was very helpful for us to improve our visibility and give more data. And what we did, we exposed pod names so that it's native for users. You can easily identify your applications as pod names. And to expose namespaces because you know that pod names are unique only within namespace and there can be collision out of that. So we added this information. This is also from the cross-connect monitor walks. We added this information And with that, we had enough information for the cross-connect in order to describe that connection and in order to connect those matrix values to a very specific connection. So what we finally had by integrating with Prometheus, you can see we have queries for Rx bytes, TX bytes, and we have our source and destination pods and namespaces. You can use them as a query, and you receive the number of bytes and packets that were transmitted for those specific communication. And what's the takeaway of that? There is takeaway for us, and there is a general takeaway. For us, it was we just wanted to integrate with the others, but the outcome was much bigger because even without the SMI integration, looking at that specification helped us to improve our own observability. We found out some problems we had. For example, the VPP agent forwarding plane wasn't actually sending metrics, and we contacted their community and they fixed that for us. We improved our visibility for cross connects. We integrated. We improved a lot our observability. But what's the general takeaway about that? Integrity is a great way to provide high quality, and it's a great way to find new ideas for your project to improve it, and it's very good to keep an eye on the cloud native landscape as new projects always appear there, and new ideas appeared, and that would help a lot to be up to speed, because nowadays predicting the future is what brings technology forward, and that helped our project to keep an eye on what's going on, and that would help anyone that is compatible with the cloud native type of solutions. And with that, I want to say thank you.